Hello everyone, this is a quick video to go through the solutions for differentiating very simple terms. So let's get on with it. So remembering that there are different types of things that we want to differentiate, and here's one, here's another, and here's different. So all these three are different, but if we can put them in the same format as each other, they're all the same thing. So we can look up here that 3x squared is something times x to the power of something. If I think about 12x, it's not quite the same because, okay, we've got the number in front, but we haven't got like a power. Like what would that be? And that would be a 1. So anything on its own there is to the power 1. And then lastly, the hardest one is 2. So where we have a number on its own, like we're clearly missing quite a lot, or we're missing an x. But the only way to get an x is to put it there and have a power such that it reduces to 1. So anything to the power of 0 is 1. And now we have our same format. So using that, yeah. And now we have our same format. And if you have this same format, you realize that the method is the same. It's just that there's going to be tricks because nobody wants to write them in the same format to begin with. Actually works out to be quite nice. Now, the rule is that there's a lot of people use this idea that you put it down the front. And this, in my career, has only led people to put it down the front and then leave nothing up the top. It's like them, or nothing at all. It's like they're moving it physically. So let's be a bit more careful with our language. We're not going to be moving it down the front. We're going to be multiplying the coefficient by the current index. Okay, so the 2 will be multiplying the coefficient down the front. Where did I get that 2 from? It was the current index. And the index itself is going to reduce by 1. So 2 minus 1. So I'm writing this as the full solution, but it's not something you need to write every single time. In fact, when you know what you're doing, you can just jump straight to this particular step, which is going to be the 2 goes down the front to make a 6. And then we take away 1 from the power and we leave it as 6x, because we don't write 6x to the 1. So this is using that method, okay, so that we just need to practice, I think. So the next one, you don't have to do it in full. I'll do it really the way like I would do it quickly. 3 times the 4 is 12, and 3 take away 1 is 2. And I guess we can take this moment to look at what happened. A term like a function that's just squared is going to go down to just a linear, and a function that is a cubic is going to go down to a quadratic. It's like differentiating makes it take a step down, which is interesting to note because it's useful later. Now, if it's a negative, it's the same old deal. That negative 2 goes down the front. So maybe we can write this one properly though, so we can not mess around with the negatives. Negative 2 times 5x. And now we're going to take away 1 from minus 2. Remember your number line. We're going to take away 1 from a negative 2. So we're already in negative and we're going further into the negatives. And we'll just tidy up that front. So negative 2 times positive 5 is negative 10, x to the negative 3. Now I'm about to introduce a bit of notation that we were using. If the original was f of x, then if we just differentiate it once, then we call it f dashed of x. And we put a little dash there. And with the g of x, it's the same thing, right? So g dashed of x. That's how we call it, g dashed of. And so what would this be? Yes, h dashed of x. Okay, fractions now. There's no different. We're going to do the same method. I'm going to jump straight to it though. So here we have, actually, for the first fraction and the next one, because they're unique combinations, we'll do it fully. Maybe we'll do it down here. So f dashed of x, the half is going to come down and multiply the front. So a half times 7 x, and then we'll take away 1 from a half. And a little diagram will just sort us all out very nicely. And you can see that if I'm at a half and I take away 1, I'm going to be at minus a half, because a half is half of 1, so it's the other half. And we can tidy up that front bit. Now the best way is to use fractions. If you're going to, like 3.5, go for it, that's fine. But in my opinion, like, no sleep was lost from using fractions. In fact, I think I sleep better using fractions. So I'm going to leave it in fraction form, but you go ahead and do you. All right, so g dashed of x. We're going to be okay with this, I hope. So we're going to minus a third multiplied by 6. Hopefully we're happy that it's negative 2. And then we take away 1 from the third. So it's minus 4 over 3. And that's a little thing about those. If we're going to be at 1/3, take away 1, that's minus 2/3. And if we're going to be at minus 1/3, take away 1, that's minus 4 over 3. Now this is important, like, to see how it works, because I feel like it's difficult to mess around like with these numbers in fractions. You can use a calculator, but the way I do it is I remember that 1 is 3 over 3. Now if we're talking about thirds, we've got 1/3 there. Let's call that a third. And then here we've got 3/3. Obviously that's not a third of a circle, but I'm just drawing a shape to represent the third. So in total we've got 4/3, and that's how we write the 4/3 there. And there are just some that are really useful. So if we're going to do a half, so minus a half, and we're going to take away 1, remember that 1 is 2 over 2. So that's going to be negative 3 over 2. And then negative 3 over 2, take away 1 again, is negative 5 over 2. Negative 7 over 2, etc., etc. There are patterns to this. So hopefully you don't feel so lost about this. And it's a very good reason why fractions are important. Let's step it up a bit now. Right, so h dashed of x here is 32x to the 3. And f dashed of x, now 2/3 multiplied is 18 over 3, which is 6x to the minus 1/3. Now I've got to do a lot in my head to be fair on that one, and probably it's better to write it out separately. So like 2/3 times 9, knowing that that's 18 over 3, so 6, fine. And then minus 1/3, take away 1, which is 3 over 3, which leaves me with, oh wait, no, sorry, started at 2/3. So 2/3, take away 1, which is minus 1 over 3. So all of that was sort of done in my head, and you don't take that risk, okay? So the more confident you are, the more you can do in your head and stay calm. And that's why we practice like things that are more complex, because it increases our ability to think about these abstract things in our head. Okay, so going straight in with the answers now, because we're probably feeling good. Now, it doesn't matter if there are fractions that are not very nice, and it's just part of it. Leave them as a fraction. Like if you're going to write the full middle here, like 1650, it's just going to look awkward in my opinion. All right, we've got a little bit different here. So we've got the 2. Now we talked about earlier writing that 2 in the format where we have 2x to the 0. So then we can enact our little plan of 0 times 2x, and then we take away 1. But because we have this 0 at the front, that whole thing goes to 0. So this doesn't matter about this or anything else. And the rule really is that we need to remember that when we have numbers, they reduce to nothing. So single numbers, or what we might call constants, they go to 0. Okay, we've got our other one, our other unique type. As I said, we could write it like this, and we could see that the 1 would come down. You can add it in if you want. The 1 would come down the front, and you'd have x to the 1 minus 1. Can you see what happened? X to the 0 would just become 1. It doesn't matter if you had a 12 on the front. That's like saying 12 times 1. It's just 12. So here, g dashed of x, when you have something like this, just get rid of the x. And there's your answer. Works like a charm. Okay, 40 plus 12. Write down here. Yep, 40 plus 12, yeah, minus 52. Next to the minus 5. Now, I won't talk if I don't have to, so for the rest part, I'm just going to work away. If I notice anything, I will say out loud. Okay. Actually, I need to come back. I didn't mean to write negative there. These are the first time I'm seeing these questions, just like you. So there is always an element of me wanting to do it quickly, like you would have, but knowing that that doesn't really help in the long run. So always double checking, and before I write something down, it has to feel like I'm saying my own name, otherwise I have to double check. Like I'm never going to forget my own name. So that's a kind of vibe that I would be going for in terms of, do I feel confident? And there's always mistakes. Like if you're not concentrating, if you take something for like you're not sure what you're doing, you're not doing it deliberately, and you take advantage of that. You could a mistake could easily slip in. We just don't want to mess around or take chances with what's important to us. And there's no shortcuts for this. If you've got you're doing calculations, you can go to a calculator, fine, but it's not going to help your thought process in the long run. I think there's definitely something to be said about being able to do things without a calculator and working through like the process itself and understanding structure. All right, lecture over. 80 plus 12, 92 over 3. I think I need to go back and correct one just based on that, by the way, because that's what happens when you're doing this. Get distracted easily. Right, so 4 times 23 is 92 divided by 3, and then that's third good. So back here, you're probably like, oh, I didn't get that. I feel like that's around here, right? So 5 times 19 is 50, 95, but I didn't write the 2. Now, I'm trying to do it in my head, and that's not always the best. Like when they are this simple, you think you may be slipping out and not thinking properly. So if I do 18 again here, and I did it properly, so I'm not going to I'm not going to forget what's going on or just not see it. If you do it in your head, it's harder to visualize. Writing it out like this, maybe there's a lot less chance that I'm going to miss the fact that there was a 2 down there. So you see what I'm demonstrating now is like I've realized that there's something wrong with what I'm doing. I'm not going to suddenly get relieved that I have the answer. Hey, that's it, moving on. Whoa, got through that. I'm going to come up with a strategy that for in future I'm going to use to avoid that. Right? So active learning, not passive. Maybe I change that to 3 over 3 just to make sure. 5 take away 3. Wait, is it? No, it's 2 over 2. Taking away halves, which is 3 over 2. Okay, happier with that. That's what I've got written down. It's possible. It's possible to happen, but just model it on that, right? I think making a mistake and it having to be right all the time is where we get maths anxiety. Okay, so g dashed of x. Oh, this is nice. Look, when the fraction works really well, we have a negative, but the half of 24, because it's an even number, comes to a nice integer. Ta-da! H dashed of x equals 8 times 25, which is 200. Plus 18, 78. Now I won't forget that 4, but I could have written it out in full, or in quarters actually, so that's going to be negative 1. So it's at this point, you'll notice I'm not really bothered about these fractions, just leaving them, because they are what they are, and I can deal with that just fine. So don't worry about that. G dashed of x is equal to 27 over 5, x to the minus 4/5. H dashed of x equals, oh come on now, 740 plus 56, 109, it's negative 196. There's a way of looking at that, so 7 times 4, 7 times 7, 4. Yeah, I suppose like 7 times 7 times 4. Maybe it's easier that way because like this is 28 and there's 49 times 4. I can double check that way. So 4 times 50 would be 200. But I'm missing a 1 for every time I've multiplied, so take away 4. Happy with that. X to the negative 8. Oh dear, 180 plus 81, 261, I think. But you know what to do if you're unsure, is you do it off to the side. I think the best way of doing it is to partition. So we're going to multiply like each individual part, like so, and then add them up. Yeah, 261. Partitioning is an open way of doing the rote methods, which are abstract and algorithmic. Nothing wrong with it. Nice, g dashed of x. Because it's a number, it just goes to 0. Happy day. All right, we'll finish on the best letter in the alphabet, H. H of x, h dashed of x is 155 over 3. Yep. X, and then this in third, so we're going to take away 3, so 2 over 3. Yeah. And there you have it. That's how you differentiate. So these are very basic. Okay, so we're looking at ones where A is all there is. Where we're looking essentially where B equals 0, and let's put it here. Different color, let's use red. We're looking here where B equals 0. In other words, that's a numerical term, that's 2. We're looking here where B equals 1, and we're looking at where B is more than 1. This is really it. And there's nothing else to say about that. If you have any questions, just put them in the comments below. And if you're ready to move on to the next sort of round of this, then fine. If not, this is your first step into differentiation, and that's how you do the basics.